Hi, folks. My name is Jamie Kostelnik, and thank you for tuning into the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with contributions from Matt Thomas and Stephen Slaughter. For those of you who are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We wait until the end of the presentation to take questions. Do your best to make sure your microphone is muted and your camera is turned off when you aren't intending to speak. Today, we are joined by Robert Emberson. Robert is the Associate Program Manager of the NASA Earth Applied Science Disasters Program. He has supported the program since 2018 as a center coordinator, providing satellite data and insight to a range of stakeholders before, during, and after disaster strike. He is also part of the NASA Landslide research team, where his current research focus is to better understand and model the exposure and risk faced by human settlement due to landsliding. Additionally, he is developing machine learning methods to better model spatial susceptibility to hazards and working with end users to find the best strategies to communicate hazards in rapidly developing disaster zone. So Robert, the floor is yours whenever you're ready. Thank you.
Thank you so much. I really appreciate the introduction, and I'm very grateful to be here today. This is obviously a really fantastic opportunity to talk with you all and to present some work. And this is, as I mentioned in the warm-up for this call, this is the first time that this work has seen public presentation airing. It was published during the pandemic, and we were pretty excited at the time, but I think because of a lot of the meeting restrictions, we weren't able to shop it around as much. So this is I was thrilled with the opportunity to present. So I'm going to talk today about some of the work we've done with the NASA Landslides team and a little bit about like the way in which we're trying to characterize where landslides sit in the landscape. And I'll start off with a brief outline of what the presentation is going to look like. I'll touch a bit upon my background and prior research that's led me to this point, just to give you a grounding on who I am and why I guess I'm worth listening to. Then a bit about the landslide inventories that have like built towards this work that we've been developing, as well as the specific research questions. Then the more bulk of the talk will be focused on the topographic analysis of where landslides have occurred in the landscape and why that matters and what the importance is, I guess, for both hazard and susceptibility. And then finally, moving on to a discussion and sort of future work of what the findings are, what the key results are, how we can expand our analyses in future, and how this connects with other work that myself and other members of my team are conducting right now, and potentially all of you. But first, I just want to say thank you to my co-authors in this study, Pukara Amatia and Dalia Kirschbaum, who are part of the NASA Landslides research team. Dalia now leads the Earth Science division at Goddard, so she has lots of different strings to her bow. Those guys are both based at Goddard with me, and then Odan Mark, who's based at the University of Strasbourg in France, and Hakan Tanyas, who during this study was based at NASA Goddard, but he is now working at the University of Twente in the Netherlands. I think many people will be aware of both of the other of all of these guys who've I think had a chance to maybe present to this team at some point in the past. But yeah, I want to credit all of them for their hard work on this work as well. So starting off with some background, the image here is a landslide some of you may recognize from Central America, from Hurricane Iota, to give a sense of the importance of landslides and why we should care about where they're impacting, not just where they're starting off. And I'll come back to that thought in a little bit later, but just sowing it in your minds right now. So a little bit about me. I have a PhD in geochemistry and how it relates to landsliding. This is me in a mountain belt in Taiwan, looking at the water filtering out of a large landslide body, trying to understand why it's so discolored. The short version is that landslides are like coffee grinders and they create huge amounts of fresh surfaces for chemical weathering. After that, I worked briefly as an editor in HGS, so a little bit in science communication. And then my postdoc was working with the NASA Landslides team, developing our understanding about population exposure to landslides, conducting large-scale and local-scale susceptibility and hazard analyses, particularly with kind of in data-poor regions, and that was with Dalia Kirschbaum and the Landslides team. More generally, the work I've conducted at NASA in the last 5 years has been looking at exposure and the impacts of landslides at global and local scale. These two images are taken from the Rohingya refugee camps in Bangladesh, where we worked with some UN agencies to understand and provide information about where landslides have occurred and what that might mean for where landslides are likely to occur. So a little bit of local scale susceptibility modeling in places with basically no data. that was work that was scaled up to thinking about susceptibility at a larger scale. And it's something that the susceptibility analysis has been a kind of a through line, particularly associating with like where landslides occur in the landscape. That's been a kind of a key part of my research throughout my career. Now I serve as the Associate Program Manager, one of several for the NASA Disasters Program. My work there is more programmatic to kind of determine where funding should go and how NASA can spend its resources to support disaster response. Alongside that work, I have current research projects focusing on soil erosion and another on extreme rainfall and how to forecast that several months in advance. If you're interested in touching base on that, I'm happy to kind of talk more about that offline. It's not what I'm going to talk about today, however, but just to give you a sense of where I come from. The exposure work that I mentioned, this is, I guess, the key outcome of one of these pieces of work is looking at where people around the world are impacted by landslides. Now, many of you will be aware that inventory-based analysis and report-based analysis of where landslide impact could occur is limited often in places by the availability of reports, and particularly English language media misses out a lot of the global south. This exposure analysis was based on the NASA LASA model, which some of you may be familiar with. It's essentially a global scale statistically based model that estimates where landslides are likely to occur based on satellite rainfall data. So we use a susceptibility model, global susceptibility, and a satellite rainfall input to provide an estimate of landslide hazard. And that was married with a global population data set here to estimate kind of long-term exposure to landslide hazard. And the key point is that, again, in the global south, you have all these places, particularly sub-Saharan Africa, Indonesia, and parts of South America, where we don't really have reports of landslides, but we do know that there is clearly a lot of exposure. So that was a nice result that came out of that. That led to further work to analyze where landslides are likely to impact people. Particularly, this is
what's going on.
Oh, sorry, so I can hear someone in the background. I don't know if that was a question. Hearing nothing, I'll keep going. Just saying that this work is has extended to looking at exposure of people as a function of El Nino, and this was work that was published more recently, looking at how exposure to landslides around the world in different different districts around the world is a function of the El Nino Southern Oscillation. The short version of this figure is that blue areas have higher exposure to landslides during La Nina conditions, and red areas during El Nino conditions. And this is a first attempt at quantifying this. This matches up well, even though this is a statistical model, it matches up pretty well with the limited data on fatalities that we have from sort of sub-regional level around the world. And again, if you're interested in this kind of work, I'm happy to talk more about it. But all of these sort of landslide analyses rely upon data sets of where landslides have occurred. Some of those, and particularly the NASA LASA model, relies upon points associated with landslides that are reported, and we know the location and the timing with some degree of accuracy. But what is potentially more useful for a lot of the local scale analyses, and particularly susceptibility analyses, is really detailed mapped inventories of where landslides have occurred, and particularly associated with extreme triggering events, so earthquakes or extreme rainfall events. And event-based landslide inventories are now, as we know, widespread. USGS maintains a fantastic archive of earthquake-triggered landslides that feeds into the ground failure model. Rainfall-triggered landslides, something that I focused on more, and so I had more, I guess, more experience with. There are a lot of these inventories out there, but I think one message is that they are less centralized. A lot of different groups have different inventories that are used all over the place from different triggering events. And they're not really kind of pulled together consistently, or at least the studies that have tended to focus on individual inventories rather than a kind of compilation. So that's the question. One of the questions we went into this with was, we know that there is a wealth of information contained in all of these individual event-based inventories. And the question was, how can we exploit this? What can we learn from these inventories in a compilation sense? So this is an example from, it's now the video is running. This is the global hazard model from the NASA LASA model. And we can just watch this as the hazard in pixel by pixel data occurs. And once we get through the first year, you'll see appearing a number of dots, and those are the report-based landslides that fill the global landslide catalog, which is the NASA landslide catalog. Now, these are individual points. We have a lot of data on those individual points, but what they don't tell you necessarily are where all of the landslides that occurred in those specific settings might be. So by that, I mean, let's say you have a very large rainfall event in southern India. Well, you know that there was one large landslide that caused a number of fatalities, but you don't know where every landslide happened. And so this is, again, emphasizing that there is a lot more potential data encapsulated in these large-scale mapped inventories. And again, I think I'm probably preaching to the choir here, but point-based inventories and polygon-based inventories have a very different kind of message than just these kind of like report-based inventories. With that question in mind, we also went into this with an with a new tool, but I mean one that I think again is probably familiar to some people, but I'll go over it briefly. And this is the semi-automatic landslide detection system. Pukara Matia, my colleague, has developed this over the last few years. In common with many different landslide mapping systems, this provides a way to effectively map landslides at a large scale from both moderate and high resolution satellite imagery. It segments the images and creates objects, and those objects essentially are polygons, and using a training set of data and a DEM, it determines which of those might be landslides and which are not. Obviously, there is a user-driven component to kind of correct the final outputs to ensure that everything is a landslide, but it's quite an effective way of creating larger inventories of landslides in a time-efficient manner, rather than, which I've experienced many times, being the intern who hand maps 50,000 landslides with an ArcGIS by tapping around with a polygon. This system, I would love to give it more time to present on this, but this is because really exceptional work. It runs on open source toolboxes and relies upon, again, open source packages for Python, can run in Linux and Windows, and we're now kind of systematically running it for the NASA Climate Computing Service. There is a training available for this if anyone's interested in learning how to use this system, and a paper is co-authored with some people from USGS, and again, let's talk about that, explaining how it fits with other kind of landslide mapping methods for the recent extreme rainfall and earthquake event in Haiti. So again, this is one of the tools we've used. So here's an example of the outputs. Again, this will be familiar to many people, but this is an example of a landslide inventory from Vietnam. This was actually created after the paper that I'm going to talk about today was published, but this is a useful example of the tool used to map thousands of landslides from planet imagery. And you can see a blown up image here that shows the location of landslides and the polygons that have been created in red. Naturally, this doesn't capture absolutely everything, and it does require hand correction to pick up some things that may have been missed on the first pass. But again, it's a useful tool to start kind of building large inventories and a large number of them. So this was, the sort of beginnings of our work. Whilst I'm thinking about landslide inventories, I want to also sow the seed again that we have to think a bit about where or what part of the landslide is important for different parts of the landscape. So I'm saying sources versus deposits is the title of this slide, and it's illustrated by this image from Taiwan, where you can see this very large landslide has occurred, and the impact on the road below and the terraces below is very severe. But that's not where the landslide was triggered. The landslide was triggered, hundreds of meters above, and so the inventories that do distinguish between scar and deposit are invaluable, because those are the ones that enable us to really examine the big differences between the source area and the runout area, or like the deposits area. Delineating between those two areas in a landslide is time consuming. It requires expert knowledge of what the landslide looks like, and ideally kind of field-based validation. So not every inventory has that type of kind of information contained, and it can be kind of difficult to kind of extrapolate and build large analyses based on this assessment. But it's an important thing to kind of distinguish with, because the source of a landslide tells us about the susceptibility, particularly if we're trying to extrapolate to a more general context. But the deposit, or where the material ends up, that's what's important for hazard. So if you care about exposure, if you care about risk, you need to know about both of these things. And at least we can try and distinguish between them. And if we can distinguish between them, then we can build a more effective picture of what might be important for landsliding in different landscapes. So that's all kind of a rambling introduction to where we're at, but I want to give a succinct kind of a sort of summary of the research questions that we went into this study with. We know that there are lots of inventories out there, and we can create more using our landslide mapping tools. With these compilations of inventories, can we see consistent patterns in the topographic location of landslides? Is there something that we know using very finely or moderate resolution data? Can we say something about where landslides are likely to occur in a landscape, and what distinguishes between the topography of source areas and deposit areas? Those two things, again, as I mentioned, can be considered separately. And the best thing, and then the sort of summary of those 2 points is, how can we best exploit inventory data, these large-scale inventories, for susceptibility and hazard assessment? So that's the key messages, the key things we wanted to determine for this study. So this is focused on topographic analysis. This image, of course, shows some of the most extreme topography in the Earth, and I wanted to use it from a space-based image to shamelessly plug my agency. But again, I think the bulk of this is going to be focused on topographic analysis, but we will touch a little bit on the way in which we can think about this for non-topographic variables that might affect landslides as well at the end. So we started off with a number of pre-existing inventories. These were all from a number of different storm events around the world, particularly from, I'm showing 2 examples here, one from Dominica from Hurricane Maria, one from summer storms in near Hiroshima in Japan. The intent was to find a number of different inventories that captured differences across the world in terms of both lithology and potentially triggering rainfall, to kind of get a sense more of what is out there. All of the polygons were cleaned to remove debris flows across all of these. So the Dominica image actually here is shown including debris flows, but those were removed in the final analysis to strip those away. Obviously, 10 is not enough to really capture the potential global extent of both climatological regime, lithology, triggering event, but it's a place to start with, and these are at least consistent in terms of having a very large number of landslides, and also consistent mapping, essentially, I guess, mapping robustness would be the best way to put it. All of these have been hand corrected. All of these have been mapped with imagery of at least, I think, 10 meters or better, other than there is one input. I'll come to that later. Here is the kind of locations of these landslide inventories. The red points are the 10 prior inventories. So again, we have 3 from South America, 2 from the Caribbean, and several from Southeast Asia. And then 6 new inventories that were created just for this study to kind of capture both different landslide triggering events and also a number of different locations around the world, some of which are in these more data poor regions that have not previously necessarily been widely reported. You'll note that there are extremely large parts of the world that are missing inventories for this study. That is not by design. That is, I think, just by we wanted to start somewhere and then work with what we had. And there are obviously a lot more inventories that are particularly out there for the United States and Europe as well. This study could absolutely be expanded to include those. I think this was a reflection of, and I'll touch on this towards the end, 2 studies that were being done at the same time, looking at both at the topography, but also at the triggering events. And we were trying to make sure that those were two corresponding studies. And so we are aware that there are places where we'd like to touch on more and expand this to in future. So in terms of lithology, as I mentioned, we have a fairly large variety. The bulk are in yellow and gray, are sort of sedimentary / metamorphic, particularly metamorphic from kind of, I guess you would describe them as ocean edge mountain ranges, particularly from sort of the Pacific Rim. And then we have a number from volcanic terrain, and again, this is both acidic and basaltic kind of volcanism, and I think 1 inventory from plutonic, and I'm sorry, there are 2 inventories using kind of like plutonic volcanism as well. So a fairly wide variety of landslides, lithologies that go into this. We did not have information at a detailed enough level to distinguish whether the lithologies influenced the location of landslides within each individual landslide inventory. Unfortunately, the global scale lithological data sets that we had access to did not come at a resolution that was sufficient to distinguish between one landslide to the next in individual locations. But it does at least provide us, a broad sense of lithologies around the world, and it could have, and we'll come to this later, been potentially an explanatory variable why large differences emerged between inventories, but as it turns out, that's not necessarily a very good explanatory variable. So in terms of the new inventories, these are the ones that were specifically created for this study. Some of these were using Sentinel-2 imagery. On the left-hand side, you can see one of the inventories from West Pokot in Kenya. This was an extreme rainfall event that occurred in November 2019. We have another one from Burundi in December 2019 using, again, Sentinel-2 imagery. This is also illustrates the fact that the SALAD change detection method can be utilized for Sentinel imagery as well as both Planet and Landsat. Other new inventories, we have 2 from the Philippines and 1 very small number of landslides occurring from Tropical Storm Tembin in 2018. This is using Planet imagery. And then we have another one from more north in the Philippines, from Typhoon Mangkhut, which again is a slightly larger inventory, again using Planet imagery. All of these inventories, by the way, are available on the paper supplementary material. So if you want to use these or download these to test or compare results, then do feel free. We have 2 additional, this is one more inventory from Southern Africa. This is Zimbabwe. This is the very large landsliding event that was triggered by Cyclone Idai in parts of Zimbabwe. You can see a kind of blown up part of this, the before and after imagery from high resolution Planet data in the center here. The below image shows the after imagery after the event, and you can again see not only the landslide sources but also the runout locations, and the debris flows were pretty extreme in this event. That information was obviously debris flows were excluded from this analysis, but it is potentially of interest, and we're happy to connect you with that information if you are so inclined. There was a final inventory created from southern India and near Thrissur in India from prolonged intense rain in August of 2018. This was again created using Planet imagery. This was actually part of a much larger series of rainfall events across southern India that actually probably would have been, I think, essentially covered thousands of square kilometers. And because we were mapping with Planet imagery, actually exceeded the memory capacity of even the computers we were using to map at that scale. So we restricted ourselves to a series of, to this area, which was impacted by one major rainfall period, several days of extreme rainfall. And unlike the rest of southern India, which was period of extreme rainfall that created a large number of other landslides across the region. So this one certainly could be expanded to cover more area, but that was at the time considered to be out of scope. But again, this is another question to be discussed in more detail. So getting into the details of these inventories, a first pass way to look at landslide inventories is to look at the size frequency distribution. Here, these are all plotted on top of one another. This gives you some sense of the at least similarities or differences between the sort of the type of mapping and the type of landslides themselves. So we can talk through some of the details here. The peak for the size frequency distribution tends to be illustrative not only of the landscape scale, but also of the type of mapping. And in this case, this is very true. The landslides, the inventories that had the sort of the highest or the lowest area peaks were mapped with the highest resolution imagery. So this is including one from Dominica and the landslide inventory from Hiroshima. And I think there was one other that was oh yes, I mean, it was two from Dominica. They were both mapped from Hurricanes Maria and Hurricane Erica. Those were two similarly located images that were mapped with, I think this was I'm going to say Airbus imagery, so again very high resolution. And that rollover point is reflective of that, and that the smallest landslides are captured in detail in those inventories, whereas those that were mapped with coarser resolution imagery tend to miss those. So an example here is from central Taiwan. That was the only inventory in this study that was mapped using just Landsat imagery. So coarse resolution data certainly misses a lot of those like very small landslides, and the rollover point is significantly further down in terms of area. Now, this is two things in one. Obviously, there are some locations where the rollover point is reflective not just of the imagery used, but also of the landscape scale. Like small landslides may be, or larger landslides might be more common in places with larger hill slopes. And that's also partly the reason that explains this extremely long tail and the further over rollover point for the inventory from Typhoon Morakot in Taiwan. Just to illustrate what that looks like, this is from 2009. Typhoon Morakot, for those who are not familiar, created some of the most extreme landsliding anywhere in the world. This is just part of the extent of the landsliding that occurred in a catchment. Ironically, this is also the catchment that I was pictured in at the beginning of the talk. The very large landslide that you can see in the kind of lower left is approximately 1 kilometer from top to bottom in terms of elevation. And so this is, enormous scale of landslides that created a vast amount of debris. And the very large hill slopes, in fact, some of these hill slopes are up to 2.5 kilometers from bottom to top, allows for extremely large landslides to occur. Landscapes with smaller total relief are unlikely to allow for what just simply cannot have landslides over a certain size occurring. So there is a kind of a landscape element to that kind of size frequency distribution. This is, however, not the approach we decided to take in terms of analysis. What we wanted to focus on is the importance of individual topographic variables. So I want to talk a little bit about the analytical approach we took here. So for each inventory, you can create the frequency distribution for a given variable. And in this case, we've selected slope as the simplest one to think about. The top part of this figure shows the frequency distribution for the pixels in each landslide for slope. And that is actually then normalized by the median landscape slope. So we take the median of the landscape and we normalize it by as we normalize the distribution of landslides, or sorry, the slope values by the median slope values. Then we can take the frequency of the entire topography, and that's the second figure here, calculate the topographic frequency distribution of pixel slope values. And again, we normalize that by the median landscape slope and calculate the frequency of that. We can then compare those two frequency distributions, and we can calculate essentially a ratio of the two frequency distributions. It's by both, as I mentioned, on slope or median of each parameter, and then we normalize by the total number of pixels. So we take essentially for both the landslides and the frequency of the landslides, for the landslides or the topography, we normalize by the total number of pixels in each of those categories. And that gives us a probability ratio, or at least what we've termed a probability ratio, which is plotted below. And so for each of these kind of subsets of the data, we calculate a value that is the sort of normalized ratio of the two distributions. The large points here are locations where the significance exceeds 95%, and the small pixels are where that significance is no longer above that threshold. So what we're looking for really is any relationship between the two that sort of shows us where landslides are occurring in the landscape. And what this essentially is telling us is above a value of, let's say, landslides are much more likely to occur above a value of 2 when the slope is 2 times the median landscape slope. That's probably very obvious, but this is a starting point for the overall analysis. And for an individual inventory, we can create this kind of figure. But for all of the inventories combined, we can merge those bottom figures together. And so that's the kind of approach we'll take, and we'll see that shortly. To add a quirk to that, we also want to look at the scars and the deposits individually. So what we've done is exploit the geometric approach of Domage et al. 2017, as well as my colleague Odan Mark, who worked on this extensively. Using the perimeter and area of an individual landslide, we can use globally defined areas, sort of perimeter area scaling relationships to define the specific area of a scar. Now, that means we can estimate an average scar area for each polygon. And from that, we can take the uppermost pixels from each scar area, from each polygon that would correspond to that total area. So this is an example from northern Morocco. This is from another study, but it just gives you an example of the polygons you can see in red and white of these landslides. And then the green pixels are the ones that are pulled out to essentially provide a proxy for the scar area. Now, this is not perfect by any means, and a full assessment of scars and distinguishing between scars and deposits would be much more robust if you had, for example, aerial imagery. But for those inventories where we've never had access to that imagery and we don't have experts who've covered this in the field, this provides a generalizable approach that is consistent across all of our inventories, and we can apply this regardless of this location. And it means we can distinguish, at least at a 0th order, I would argue, between the scar areas, or at least the uppermost areas of the landslide, and the deposits themselves. So this is the approach we've taken, and we then analyze the pixels associated with the scar, and the pixels associated with the entire landslide, to include scar and deposit as a way to kind of distinguish between those two. And then to look at the different topographic variables. So I'll walk you through those in the next couple of slides. So here's the first of our results. So this is just looking at slope, and we have the median landscape slope divided by the median landscape slope on the x-axis, and then on the y-axis is again this probability ratio. And you can see that for many of these inventories, and they're all colored differently, and this is a very kind of like spaghetti kind of plot, but the key point here is that a lot of these inventories collapse onto a very similar kind of distribution. And to drive that home even more, we see that when we look at where the probability ratio is essentially 1, that is at a point where the slope divided by the median landscape slope is also 1. So the median landscape slope is influencing where that probability ratio crosses the probability ratio equals 1 as well. And that collapse onto that kind of point is in part a reflection of the treatment of the data, but it also illustrates the fact that a lot of these inventories have pretty similar characteristics in terms of these two relationships, at least when they're normalized by the median value for the landscape. The next parameter we looked at was the average upstream slope. This is a little bit different to just this individual cell slope. This provides a proxy for the steepness of the areas draining into that pixel. This is obviously collinear to some extent with just slope, and we've considered that. We'll touch on that in a few slides. These images are just to illustrate what kind of is meant by average upstream angle. It is calculated for each cell, and it calculates the angle to every cell that drains into that cell. It kind of gives a sense of both slope and also the kind of intensity of drainage into individual cells. And the other reason to look at this is it coincidentally provides quite a strong relationship in terms of both scars and landslide areas, so left and right. There's actually a tighter fit for all of the inventories combined when we look at that. And again, we see that the different inventories, although they diverge at like high and low values, do again collapse onto that kind of average upstream angle divided by median average upstream angle at a probability ratio of 1. So again, same kind of collapsing onto the same points. The next parameter we considered was compound topographic index. Many people will know that as wetness index. This is calculated as the log of flow accumulation divided by tan of the local slope. And it's in many cases associated with where water accumulates in landscape and often soil thickness. In this case, we see an interesting difference between scars and the entire landslide area. And this is the first place where this is beginning to emerge. Wetness index, or CTI, is much more associated with a location, or much more clearly, there is a stronger relationship, at least, between the scar location than there is with the entire landslide area. So what that's telling us is that scars are much more likely to occur at low CTI values, so higher up in the hill slopes, versus in sort of hollows in the landscape themselves. And it's pretty obvious when you think about it, but at the same time, it's really quantifying this kind of relationship. Once again, both of these kind of relationships are sort of collapsing to this 1-to-1 value. Again, we'll come to this in a second, but it's just wanted to illustrate that is part of something to observe here. The next parameter we looked at is topographic ruggedness index. This is closely associated with roughness. It's the root mean squared difference in elevation between a central pixel and each of the 8 neighboring pixels. Again, we see a pretty strong relationship between the scars and the slopes, with higher roughness tends to be associated with higher landslides likelihood in those locations. Probably a better relationship for scars than it is for deposits. Next up, we looked at relief. This is topographic relief calculated over a 1 kilometer window. Not such strong relationships observed here, although the entire landslide is less likely to be found in places with very low relief. But again, I think relief is only a limited predictor, it seems like, of the location of landslides, particularly of scars. And it's tend not to be such a strong predictor, as we'll see in a few slides as well. The next parameter we considered was topographic position index. This is sort of widely used amongst some groups, but not everywhere. So I'll give a brief overview. Topographic position index provides an assessment of where in the landscape something might occur. It provides a negative value when it is calculated in a kind of convexities, and a highly positive value I'm sorry, other way around. Concavities provide a negative topographic position index, and convexities provide a very positive value. So you can also calculate this over different, I guess, wavelengths or different distances. Looking at very large distances, you can calculate a very, you can look at very large convexities or very small convexities, and you can essentially get different results depending on what you look at. We calculated topographic position over a 2,000 meter distance and also over a 300 meter distance, which is in line with what has been done in previous studies. I just will state that the 2,000 meter radius topographic position index provided 0 illustrative results, but the short wavelength or 300 meter result was more illustrative. That's what you see here. This is the only one of these parameters that was not normalized by the median in the landscape, and that's because this is already it's kind of a normalized parameter. But the probability ratio for scars and versus the entire landslide area is very different. Their relationships aren't necessarily as strong, but in some inventories, we see that for positive numbers, so this would be for, I guess, convexities, I believe, landslide scars are more likely to occur, whereas at negative TPI values, so concavities, these hollows in the landscape, the entire landslide is more likely to be found. So again, that makes sense, is that scars should be occurring on convexities in the landscape, and the deposits would occur in concavities or be found in concavities, but it's a nice illustrator of that, and we can see this difference more clearly in a couple of slides as well. Because a lot of these parameters are associated with one another, and slope, for example, is a strong predictor of average upstream angle. It's a very strong predictor of roughness. It's also, associated with relief. We wanted to do some kind of approach, or we wanted to find a method to essentially try and reduce the collinearity and assess the individual importance of these individual variables. So this rather complex figure illustrates the approach we took in some ways, but I'll give a kind of overview as well. We used the lasso-based selection method to regularize all variables for a generalized linear model to reduce collinearity, and then the regression coefficient for each of those input parameters was assessed for each inventory. And so what you're seeing in this image is the color bars for each of the inventories, and where you see a color bar, it illustrates the importance of that variable associated with the location of landslides. And on the left is for scars, and on the right is for the entire landslide. So what you're seeing is slope clearly is important for almost all of the inventories, and in a positive manner. So higher slope means greater likelihood of landslides, both scars and deposits. Average upstream angle is only important when slope collinearity is removed for a handful of those inventories. Wetness index, CTI rather, has some importance for some inventories. More negative wetness indices are relevant for landslide scar location, but also for some deposit locations in some of these inventories. And then, to a lesser extent, roughness index, as well as ruggedness index, as well as the topographic position and relief are also somewhat relevant for some of these inventories, but not for all. So again, this was a way to kind of illustrate that slope is the predominant factor in most of these locations, but there are strong influences from some of these other factors as well. This kind of analysis would be more relevant to conduct sort of susceptibility analysis rather than exploring individual variables, but it's important to kind of assess as part of our study. So that's the kind of results. Moving on now to touch on the kind of discussion. We want to talk about the assumptions that have gone into this study. So first off, all of the inventories we've looked at are generally focused on shallow landsliding. We've not really focused on slow-moving deep landslides. There are large landslides in some of these inventories, but in all cases, those have been triggered by extreme rainfall events, and so they're not these slow-moving events, and so there would be very different, I think, outputs if we look specifically at slow-moving landslides. But again, we are kind of capturing a large range of potential landslide regimes, from these smaller sort of shallow landslides to some very large catastrophic failures. There are obviously lithological and climatological regimes that we have not encapsulated in these 16 inventories. There are a lot more inventories out there. Here's one that we produced in the last, since this study was published, from Vanuatu. And there are, I would say, I think now there's like probably 20,000 published in the Mekong region by my colleagues. Probably 20,000 landslides spread across 16 inventories, I think, in the Mekong region. there's not 20,000 inventories in the Mekong region. But a number of more inventories have been published, and as the years go by and high resolution imagery is widely available to lots of different groups, more and more of these inventories are available. And so again, this kind of analysis could be expanded. And we could also potentially think about how to expand this to non-event triggered inventories. So by that, I mean sort of monsoon rain, for example, triggered over a number of months. Like, would that look different to the way in which rainfall triggers over, well, where the locations of landslides triggered by singular extreme rainfall might occur? So these are all potential questions to think about in terms of whether our inventories are representative enough. The next question is whether the DEM resolution that we use, and so this was using SRTM or NASA DEM, the 30-meter resolution DEM that's globally available, whether that influences our findings. The figure here is the landslide area plotted against the cumulative fraction of total area. So it's a little bit like a companion to the frequency area plot that you saw, size frequency distribution you saw at the beginning. There are some inventories, the two brown lines on the left-hand side from Japan and Dominica, where there are a lot of landslides that sit below the cumulative, below the kind of the size of an SRTM grid cell, so below 90 square meters. So in some of those cases, more than half of the landslides are below that scale. And so, like, if we're looking at a singular pixel, are we going to get any really useful information? We could use high resolution DEMs to assess this, but we also tested by using, I guess, a linear interpolation of the DEM and making it more fine resolution in the crudest way possible to test whether there was any difference in our findings. So this is what this figure shows. There's a lot of information captured here, but the key differences to look for are the brown is from Japan and the pink is from Dominica. And the triangles are where is the original resolution, and the circles are when this resolution is increased to 10 meters using linear interpolation. The short version is that we see differences, but they're not very pronounced between the inventories when you draw out these differences in when you create these artificial kind of the artificial DEM interpolation. So the short version here is that for these very fine resolution mapped inventories, DEM resolution probably does matter, and I think it is important to capture as fine resolution DEMs as possible. But for these two inventories, it doesn't look like it makes a vast difference to the overall shape of the relationships. So the key messages here, and I'll walk through this sort of bit by bit. The point where relative landslide likelihood exceeds the topography likelihood is the landscape median. So that's the point I was kind of making across these individual landslide individual places, is that the 1-1 point is where landslide likelihood is more likely or less likely than the topography frequency distribution, and it's at that point when it's like normalized by the median. Now, again, this is a function of the way in which we've treated the data, but it's a way to determine whether your inventory corresponds to these kind of relationships. If you suddenly diverge from that, then there is potentially a characteristic that you've not captured, or there is something potentially that is missing from the inventory itself. And so it's kind of saying that landslides occur in a point where that is like set by the terrain, just the averages of the terrain. Now, we still know that more landslides are likely to occur in steeper terrain, like the absolute number of landslides, and the overall likelihood will still depend upon the absolute parameter values. Like steeper slopes will still create are likely to create more landslides. But the location where they occur in a given landscape is very much dependent upon the median of that landscape. So again, it's a way to think about comparing diverse landscapes. And this is consistent across all of the lithologies that we assessed. The other key message is the way in which we think about scars and deposits. So I mentioned for wetness index and topographic position, we could see differences between the scars and the deposits. And here, we've divided scars by deposits, basically. Instead of looking against topography, we're comparing scars and deposits. So on the higher part of this figure is places in the landscape where scars are more likely, and the lower part is where deposits are more likely. And roughly what this illustrates is susceptibility versus hazard. So parts of the landscape where the wetness index is low, so higher up in the hill slopes, are more likely to be susceptible to landslides, whereas lower in the landscape, where wetness index is higher, is more important for hazard. In other words, where deposits might impact roads, population. And the opposite is true for topographic position index. Again, it's like The convexities are where landslides are likely to initiate, and the concavities are where landslides are likely to accumulate, or deposit. This is probably obvious to everyone, but it was important to quantify this as part of the study. And because we have the kind of differentiation between skarls and deposits, we were able to do so. This is important as well because it's more relevant to do this at a pixel basis rather than a slope unit basis. Because without refining the slope units to kind of differentiate between the source and the deposit areas, it's harder to kind of distinguish between those different characteristic topographic parameters. So whilst I am a strong proponent of slope unit analysis for landslide assessment for lots of different reasons, I do think it's worth continuing to look at the pixels themselves just to kind of capture these differences between potentially the top and the bottom of hill slopes. Let's put it that way. The next steps, I just want to give a very brief overview and some thoughts on thinking about additional static parameters. Obviously, land cover is another parameter we can use global data for to think about what land cover types might be more likely for landslides, whether forest cover makes a difference. Slope length is a factor that is widely considered in soil erosion studies and something I'm working on. This is an example from Europe, looking at both slope length and steepness, but whether longer hill slopes, and that doesn't just mean relief, but whether longer hill slopes are more likely or less likely to trigger landsliding, to have landslides located there, I apologize. And then erodibility of the soil, again, another parameter that is widely used in soil erosion studies that could be considered as part of the large-scale assessment of landslide location. As I mentioned, this was also a study that was done in conjunction with a second study, and that was to look at the triggering rainfall that was associated with those landslides. This is a shameless plug for the paper that went alongside this, that was led by my colleague Odan Mark. He looked at the inventories discussed here and determined whether the satellite rainfall products that are available, so MSWEP, iMerge, and GSMAP, are of any use in determining the location of those landslides, and both in terms of time and space. The short answer is that in many cases the answer is no, but in some cases the answer is yeah, it can do quite a good job. But there are also some differences between the different rainfall products, and generally we find that there is no good product specifically for landslides, but some do better than others in some locations, is the short message here. I encourage you to read this individual study separately. I also would encourage you to invite Odan to give a talk, but just to say that we also looked at the triggering rainfall associated with these inventories in a separate piece of work, because this was a much larger effort than we had time to do in the topographic analysis. And I want to give one final shameless plug to the idea that there are now lots of inventories out there. We at NASA have been maintaining the Global Landslide Catalog, which is now also has a community contributor element to it. This is mainly for cataloging individual landslide locations, so point and report-based inventory. It's a report-based inventory, essentially. It's not entirely appropriate for cataloging large inventories from singular events. But as we have these more and more inventories, and as I mentioned, there are 20,000 landslides in the Mekong that were mapped across a number of different sites by my colleagues. And there are huge numbers of more inventories across the world that are being produced. How we archive these and who's doing that, I think, is a very important open question. I know that lots of different people would love that to be done. I know that it is a global problem, and I think it's important to discuss as a team. I know that NASA is discussing with the British Geological Survey and USGS as well. I think this is an interesting discussion. I do not want to try and point fingers at anyone here, but I encourage everyone who is interested in this discussion and how to archive landslides to talk more about it as a team. So thank you for your attention. I really appreciate your time. I would love to take any questions or comments. If you don't have time during the talk, please do reach out to me via email. I hope that I'm able to address any thoughts you have. So thank you again.